So this lecture we will get started on the postulates of quantum mechanics. So the subject of this lecture and the lecture after today's also would be dealing with the subject of the postulates of quantum mechanics. Okay. My screen sharing is causing problems from the get-go. Sorry about that. Okay. So just like classical mechanics as a subject is based on a rather simple framework. Right? So what is the framework upon which classical mechanics is based? Basically, the dynamics of a particle in classical mechanics, the dynamics of a particle under the action of a force, is basically governed by two dynamical variables, right? So what are the dynamical variables? The dynamical variables are the position and the momentum. So in Hamiltonian dynamics, for example, or Lagrangian dynamics, the variables are different, but they're interrelated. In classical mechanics, it is a rather simple framework in which the dynamics is governed by two variables, two dynamical variables. These are usually taken as the position of the ith particle, Qi, and the momentum of the ith particle, Pi. Okay. Now, once we decide that if we know the position and the momentum of all the particles, then the dynamics is specified in the sense that if you know what the external forces are, in other words, if you can write down what the Hamiltonian function h is, you know how the position and momentum of the particle vary as time varies. So Qi dot is given by dh over dpi, and Pi dot is given by minus dh over dqi. Okay. So these are the two fundamental equations. They are called the Hamilton-Jacobi equations. Hamilton-Jacobi equations. And these basically govern the dynamics of the particle in question. So, excuse me. What does this mean? This means that once I specify Q and P at some point and I know what the Hamiltonian function is, then I can use these two equations to figure out the dynamics at every other interval of time. Right? So all future times, I know what the position and momentum of the particles are because I know what the forces that are acting on the particle is. That's all. This basically specifies everything you need to know about the system. Now, the connection between forces and Hamiltonian function, obviously, as you know, is that if you know what the force is, you can figure out what the potential energy is, because force is the gradient of the potential energy. And if I know what the potential energy is, I can construct the Hamiltonian because it is total energy, which is kinetic energy plus potential energy. So you pretty much know everything about the system. Now, the same classical mechanics can be reformulated in different languages. In the traditional introduction to classical mechanics in terms of Newton's law, you start by saying that the force is equal to the time rate of change of momentum. Okay, again, this is a second order differential equation because this can be written as d square r over dt square, and you need two initial conditions to figure the r out. So the goal of classical mechanics viewed this way is to figure out what r of t is. Right? Once you know r of t, you know the trajectory of the particle at any instant of time. Or I can view everything in terms of Lagrangian mechanics, where the dynamical variables are position and velocity, generalized velocity Qi and Qi dot instead of Qi and Pi. So however you, you formulate classical mechanics, it is a set of simple laws that tell you what is the trajectory of a particle that is acted upon by some external force. That is all. Okay. Now, so simple doesn't mean it's easy. The whole subject of classical mechanics is extremely useful, and classical mechanics explains pretty much everything that you can observe in an experiment, unless you do some specialized kind of experiments. It explains, motion of planets, the motion of balls, the motion of this and that. As long as you're not talking about subatomic particles, the dynamics of subatomic particles, or particles moving at velocities very high compared to the speed of light, comparable to the speed of light, then classical mechanics seems to explain everything well. Of course, as you know, classical mechanics does break down at some point, but it is based on a rather simple set of laws. Okay, I can view it as a second order differential equation in the form of Newton's law, or I can view it as two first order differential equations in the form of the Hamilton-Jacobi equations. Now, once I know Q and P, I can construct everything else that I can measure in a lab, right? Why? Because everything else that I can measure in a lab is some function of Q and P. The total energy is the kinetic energy P square over 2m plus the potential energy V. Angular momentum is R cross P. I know position, I know momentum, I know angular momentum. I can construct all the observables, everything that can be measured in a lab. These are examples of observables, things that can be observed. Okay, observables are things that can be measured in a lab. Okay, that's the typical literal translation of the word observables. Okay? So I know how the trajectory of the particle is under the action of the forces, and I know what the energy of the particle is, what the angular momentum of a particle is, and so on and so forth, right? So if the total energy of a particle is conserved, then this is something I can actually experimentally test. I can measure the total energy of the particle at this point, and then after 1 hour, I can measure the total energy. And if it is the same, then I can conclude that the energy of the particle is conserved. It is not changing with respect to time. So on and so forth with angular momentum and things like that. And then in your classical mechanics course, you will find that whenever something is conserved, there is an underlying symmetry in the theory. And we will also expound this concept in quantum mechanics. In quantum mechanics, this subject is actually much richer than in classical mechanics. And it turns out that in quantum field theory, which some of you might be interested in understanding later, this concept of symmetry takes an even more interesting form. So as you keep learning more and more physics, symmetry is something you will be coming back to again and again in richer and richer forms. So it's something that you should be on the lookout for. Anyway, so I don't want to talk much about classical mechanics. All these aspects of classical mechanics will be covered in that particular course. Let us talk about quantum mechanics. So what is the framework upon which quantum mechanics is based, right? This is the question that we want to answer in this course. Well, notice that even when formulating classical mechanics, you have to take certain things for granted. So, my slide share is causing me a lot of problems today. I apologize about that. I might have to keep sharing and resharing quite a few times, it turns out. Okay. So what is the thing that you can measure, and what is the thing upon which your understanding of the subject is based on? So notice that, let us take Newton's second law. So this equation, F equals dP over dt. Okay. So give me just a second. Sorry. There seems to be something. There seems to be something very bizarre going on with my internet connection. So I'll try to fix it and then reshare. There we go. Okay. Okay. So notice that there is nothing upon which Newton's second law is based on, right? So this is something that is very important for you to understand. Newton's second law, which says that the force is the time rate of change of momentum, is a fundamental law. So a law is a very important word in physics. A law is not something that uh, it is the most basic of all the things. Right? You can deduce other things from the law, but I cannot derive Newton's second law. Right? Nobody told you how to derive Newton's second law because there is no derivation for Newton's second law. Now, if there is no net force acting on the object, I can derive that the total energy of the particle will be conserved. If there is no net torque acting on the object, I can derive that the total angular momentum of the object is conserved. If there is momentum conservation, I can also deduce that there is a symmetry behind this momentum conservation called translational symmetry. These are all things I can derive or deduce based on something fundamental. And that thing that is fundamental to the subject is Newton's second law. Okay? So Newton's second law is the foundation upon which the entire subject of classical mechanics is based on. So just like some Newton's second law, there are certain things that are fundamental to quantum mechanics. So I'm going to be talking about a series of postulates of quantum mechanics. And one thing that I cannot possibly answer is why. Why is it that you are telling me that this is true? For the same reason that I cannot tell you why Newton's second law is true. All I can do is that if I take Newton's second law to be true, then I can deduce a whole bunch of things and I can go ahead and measure things in a lab and show to you, demonstrate to you that Newton's second law is indeed true. The fundamental assumption that I have is indeed true because all the things that flow from that law can actually be tested in a lab. Okay. Similarly, quantum mechanics is also based on, we don't call them laws, but we call them a set of statements. A set of statements that I cannot prove to you on the basis of anything more fundamental because the subject is constructed on the basis of these things. And these are what I will introduce to you in the next 2 to 3 lectures. And these are called the postulates of quantum mechanics. We will first talk about the first postulate of quantum mechanics. First postulate. Now, my job is to try and impress upon you what this postulate means and what this postulate does. What I cannot do is tell you why this postulate is true. Okay? Any answer that I can give to this question is basically, a fake answer because there is no way I can prove this on the basis of anything else that I know. The first postulate of quantum mechanics tells you the following. The state of a physical system at any time t is defined by specifying a vector or a kit I'll just call it vector and not kit. Vector belonging to the Hilbert space of the system. Okay. Now, Hilbert space that I have written down here is basically an example of a linear vector space. This is a linear vector space. Okay, I'll define what a Hilbert space is as we go along. The first postulate tells you the following. It's a rather abstract postulate. It tells you that if you want to know the state of a system in quantum mechanics, you ought to be able to know what is this state vector. In the linear vector space in which the physical system resides in. Okay. Now, this is why we started this subject by delving into the subject of linear vector spaces, because it is fundamental to the construction of quantum mechanics. Okay. The first postulate itself tells you something very abstract. It's very difficult to wrap your heads around this. But don't worry, as we keep going on, there'll be more postulates that confuse you even more. So the first postulate will be actually simpler in retrospect. First postulate tells you, look, suppose if I want to understand the motion of an electron, okay, suppose if I'm applying an external electromagnetic force on the electron and I'm looking at the motion of the electron, then classical mechanics tells you that the motion of the electron can be understood, the state of this system can be understood if I specify the position and momentum of the electron. Quantum mechanics tells you, no, forget position, forget momentum. The state of the system is specified if you tell me what the state vector is that lives in the Hilbert space of the system. Now, this is something that is very off-putting, right? So what is the Hilbert space of the system? What is the linear vector space that corresponds to the system? What is this state vector? These are all questions that we will define and answer as we go along. So to give you a rough example, suppose if I take the spin as my measurement. Suppose if I want to say, so question, what is the spin of the electron? Okay. Now I can go ahead and measure this. I can go ahead and measure this, and I would get some kind of an answer. The answer that I would get, and I will also talk about the possible results of measurement. The answers that I will get are plus half and minus half. Okay. Let us say the X component of spin or Y component of spin or so on and so forth. Now, in quantum mechanics, we say that this means that the physical system resides in a two-dimensional linear vector space, okay, in which the basis vectors can be understood as plus and minus, or equivalently up or down in this particular fashion. Okay, so if this is my system, this is my linear vector space. There is no general answer to this question, but the most general linear vector space in which quantum mechanics is formulated is called a Hilbert space. LVS in which quantum mechanics is formulated is called Hilbert space. Hilbert space is one kind of a linear vector space, and I will define what a Hilbert space is once I've introduced the notion of function spaces to you. Okay, so please hold on for a while. If this is a little confusing, don't worry about this. For now, understand Hilbert space as a linear vector space, that is all. So if we simply substitute linear vector space for Hilbert space, right now you will not lose much. But of course, you have to understand that Hilbert space is a very specific example of a linear vector space. It's an infinite dimensional linear vector space in which every Cauchy sequence converges. Now that's a very technical definition, and I will tell you a little bit about it when I talk about function spaces. But once I tell you that the system is in a linear vector space, then there is an immediate consequence. The consequence is that the state vector now has to obey all the rules of a linear vector space. There are 10 rules of a linear vector space. The most important of these rules in the context of quantum mechanics is the very first rule. What is the first rule? The first rule says that if psi and phi are possible state vectors of the system, what does the rule of a linear vector space say? Then any linear combination of psi and phi is also a vector that resides in the system. So then A times psi plus B times phi is also a possible state vector. Okay. Now notice that these state vectors are not just one vector, because in classical mechanics, I apply a force, the system changes, the position changes, the momentum changes. In quantum mechanics, I apply a force, the state vector changes. So this psi, the state vector psi, is actually a function of time. Okay, it's a psi of t, because as I keep changing the time, there is a dynamical problem. The state vector changes with time. The equation, this is also one of the postulates of quantum mechanics. The equation that tells you how the state vector changes with time is called the Schrodinger equation. We'll come to that later. Right? So this is a very, very important consequence that follows from the axioms of linear vector space. And this leads us to what is called the superposition principle. The superposition principle states that a linear combination of state vectors is also an admissible state. Okay. This superposition principle is fundamental to quantum mechanics. Okay, it's a linear combination of state vectors. So it's not some quadratic combination, it's a linear combination, which makes quantum theory a linear theory. Okay. Now, if you remember, in the first two lectures, we introduced a set of sequential Stern-Gerlach experiments. So yesterday I reminded you that you should go back and revise those notes again. Today I will again remind you that you should go back and revise those notes again, because after I finish the postulates, I will revisit the sequential Stern-Gerlach experiments that seemed a little mysterious at that point, and I will explain why the results of the Stern-Gerlach experiments that we talked about make absolute sense when viewed in the light of the postulates of quantum mechanics. Okay. So again, go back and revisit those lectures if you have forgotten them. So this is the first postulate of quantum mechanics. The first postulate of quantum mechanics tells you what it is that you have to find out if you want to understand anything about the system. Now, this is a little bizarre. Why? Because you actually measure things in a lab and you don't measure the state vector, right? So you have not met a single experimentalist who says, wait, oh, okay, bye-bye, now I have to go to my lab to measure the state vector of the electron. So the state vector, even though I keep claiming that once you know the state vector of the system, you know everything about the system, the state vector itself is not a measurable quantity. So quantum mechanics has to be formulated as a series of rules that helps me understand how is it that I make a connection between this state vector and the things that I actually measure in a lab. So these are all set of things that we will talk about as we go along, starting with the second postulate. So again, the goal is to try and explain the universe around us, right? To the extent possible. We cannot explain just about everything using quantum mechanics thus far. We know that there is no quantum theory of gravity, for instance, but you can measure an awful lot and help explain all these subatomic interactions using quantum mechanics. So we need to understand how to make connection with experiments. So we will do that starting with the second postulate. And this is the last thing that I will talk about today. So let me divide this. The second postulate of quantum mechanics. This is an interesting postulate, but it won't still be something extremely radical. Every measurable quantity, that is an observable, is described described by a Hermitian operator A acting in the Hilbert space of the system. What does this tell you? This tells you that for everything that you measure from a classical standpoint, for example, like energy, angular momentum, position, whatever it is that you want to measure, in quantum mechanics, there is a corresponding operator that does the job for you. So every dynamical variable, every observable rather, every observable in quantum mechanics, there is an operator. Okay. So when I talk about position in quantum mechanics, there is an X operator. When I talk about momentum in quantum mechanics, there is a P operator. When I talk about energy in quantum mechanics, there is something called the Hamiltonian operator, which is of fundamental importance in quantum mechanics. When I talk about angular momentum, for instance, then there is a corresponding angular momentum operator, L hat. Now, in classical mechanics, these are all things that you can measure, but quantum mechanics tells you that for everything, there is a corresponding operator that is acting on all these vectors in the Hilbert space of the system. Okay. Now, this is both intriguing and confusing. Why? Because, okay, so there is an operator, but I have told you repeatedly that an operator by itself does not have any meaning, right? But position, momentum, energy, angular momentum, these are all things that have a specific meaning, right? Position corresponds to where the particle is. Momentum corresponds to what the velocity of the particle is. Energy corresponds to what is the total amount of kinetic energy and potential energy of the particle. Angular momentum again corresponds to how fast it is rotating. So these are all things that have a specific meaning. But on the right-hand side, you have some abstract operators that act on the vectors of the linear vector space. The operators by themselves don't have any meaning. So quantum mechanics should not only just tell you that all these classical observables correspond to these operators in quantum mechanics, but it should also specify the rule using which you can extract reliable, meaningful information from these operators. We will talk about what these reliable, meaningful rules are as we go along. But for now, notice that this is not as abstract as it seems. Even though position corresponds to an operator, and an operator by itself is a little abstract, there is a set of rules through which I can identify what the position of the object is in quantum mechanics. Okay. Similarly, what is the momentum of an object in quantum mechanics? I can very well talk about what is the momentum of an electron in quantum mechanics also, but it turns out that the way I specify this is using a rather probabilistic interpretation rather than a deterministic interpretation. So this distinction between classical mechanics and quantum mechanics is fundamental and very useful. And let us talk a little bit about this and stop for today, because I don't want to go to the third postulate because I want to combine the third and fourth postulate for one lecture. So I will keep claiming that classical mechanics is a deterministic theory. So maybe you already know why this is true, but it is very easy to see why this has to be true if you go to the first page of your lecture notes for today. So what is the first page of the lecture notes today? Which it is conveniently not showing right now, but I'll bring it up again. So as this is coming up, let me say that this has to do with the dynamical evolution of the system. So Qi dot equals dH over dPi. This is the equation that tells you what the position of the particle is at any future time. Okay. Similarly, Pi dot equals minus dH over dQi. This tells you what's the momentum of a particle at any future time. Now, these are what are called deterministic equations. Why? Because there is no uncertainty. See, if I tell you exactly what the force that is acting on the electron or whatever particle is, then there is no error. Apart from certain experimental errors that are unavoidable, I can make the experiment more and more and more and more precise, and I can measure the position and momentum of a particle to more and more and more and more accuracy, regardless of whether I measure them simultaneously or whether I measure them at any random time. It really doesn't matter. I'm only limited by my experimental accuracy. There is nothing the theory imposes upon the measurement of Q and P. There is no error. There is no fundamental uncertainty. If everything is perfect, you should be able to measure Q 10,000 years from now if you don't change the force field that is acting on the electron. Okay. If I know what the position of the electron at this point is, and if I know exactly the forces that are going to act on the electron for the next 100 years or so, I can predict where the electron would be 100 years from now. There is absolutely no problem with that. This is an example of a deterministic theory. A deterministic theory tells you that there is absolutely no problem in determining the future nature of the physical system. Okay, there is no uncertainty, there is no probability, nothing. Quantum mechanics does not tell you that. Quantum mechanics is what is called a probabilistic theory. This I cannot explain simply with the things that we have developed thus far. This is something I will try to impress upon you starting tomorrow. Starting tomorrow, you will slowly begin to understand why it is that quantum mechanics is a probabilistic theory and what is probabilistic about it. And to give you a hint of what is the fundamental thing in quantum mechanics that makes everything probabilistic, that is the very, very innocent looking thing called superposition principle, which tells you that any linear combination of states is also a state. This very simple looking statement actually makes quantum mechanics a very, very different kind of theory. And starting tomorrow, we will try to understand why. Starting next lecture, we will try and understand why. On Monday, we will start with the third postulate of quantum mechanics. And the third postulate and fourth postulate, sometimes they are called the measurement postulates. The fourth postulate is what is called truly the measurement postulate. But the third postulate is also intricately connected to the fourth postulate. Okay. So we will stop at this point here at the second postulate. Basically, what we have talked about today is that whenever I talk about the state of a physical system in classical mechanics, I mean measuring the position and momentum of the particle. In quantum mechanics, I mean something very different. I mean that if I know what the state of a physical system is, I know what the state vector is of the physical system that resides in the linear vector space in which the physical system is described. The second postulate tells you that for every observable in classical mechanics, there is a corresponding operator in quantum mechanics. So this in itself is incomplete. I also have to tell you how it is that we extract information from the state vector and from the notion of operators. And this is the most important aspect of quantum mechanics. And this is why I don't want to start this at this point in just 10 minutes from now. So we will talk about this in the next lecture, the third and fourth postulates. And your understanding of third and fourth postulates will depend on how well you progress in this course. So please make please pay a lot of attention to the next couple of lectures, in which we will talk about the third and fourth, the measurement postulate of quantum mechanics. And after that, we will introduce a Schrodinger equation, and then we will switch gears and then talk about function spaces. And once I finish my lecture on function spaces, that will sort of wrap up the introduction to the theoretical construction of quantum mechanics. And after that, we will move on to solving certain systems. Okay. So that is the plan of action. And for now, I will